Hello everyone, this is Yufeng from the Leibniz University Hannover. Today I would like to present our work to generate multi-scale building maps from area imageries. Building extraction is a hot topic in remote sensing. However, a map product as detailed as official footprint data is still hard to achieve. There are several reasons. The nearby occlusions, such as trees, and the building eaves, which leads to that the detected buildings are often larger than the footprints, and also the imperfection of imagery data. The true orthophotos are not always available. More often, it is practical to be used for topographic mapping, especially to be used to update the outdated maps. As for the topographic maps, scale is an important feature. Mapping agencies have built vector database for different map scales. However, it is not easy to be updated in a consistent way. In this work, we present a pipeline to generate multi-scale building maps from area imagery, and then we compared with existing data in the topographic database and provide directly the update proposal for the unmapped building at a desired map scale. In our recent study, we used the convolutional neural network to learn the building map generalization from existing map series. A model can be learned to compromise multiple generalization operations instead of perform them one by one. Operations such as aggregation, simplification, and elimination can be achieved with this model, which means very small buildings are eliminated, very close buildings are combined, and complex shapes are simplified for the map at a higher scale level. The input data is rasterized OpenStreetMap building layers, and the targets are generated by vector-based building generalization software change. We have compared different network architectures and select the UNet with ResBlock to be the best model. We trained the model for 3 map scales separately and achieved a very small error rate. With this, we built the following pipeline. The area imageries are first classified using land cover classification model to detect the buildings. Then the building blocks are generalized with the convolutional neural network model we have learned, and then we vectorize them and compared with an existing vector layer in the database. Then we detect the changes and provide the proposal for changes. The land cover model we have used is a network adapted based on SIGNet. The input of these networks are digital orthophotos, which including the RGB channels and the infrared channel, and also the normalized DSM, so digital surface model subtracted by digital terrain model. The ground sampling distance is 20 centimeter, and this model has 2 branches as input. The upper branch is the RGB channels, and the lower branch is the red and infrared and normalized digital surface model. The performance of the H-class land cover classification has achieved an overall accuracy of 89%, and the average F1 score 81%. As for the building, the F1 score is 94%. After generalization, the result is still in raster, but most of them are without extrusion and indentations. We first find the contours and simplify the contours with the existing module in ArcGIS, and further optimize the building shapes. We force the potential opposite edges to be parallel, as we shown on the left side figure, and also we complete the missing part at the corners of the buildings, as we shown on the right side of the figure. Let us see some results. So these are the RGB channel of the images and also the detected building blocks. We can see that the detection has covered the building pretty well. And below you can see that is the footprint data from official ArcGIS. and we performed generalizations on the building blocks and has achieved the predictions of these buildings at 3 different map scales, which you can observe the simplifications of the building outlines and also the eliminations of the very small building. And after that, we just vectorize them and convert them to a vector data. Let's look at some examples in the larger areas. So we can find first the buildings with very complicated shapes can be reconstructed very details in a lower scale like 1 to 10,000 and also to be simplified at a higher depth scales like in 1 to 25,000. And also the very small buildings has been eliminated and also near the building close to each other has been combined in a rectangular shape. So which we provide a good product which directly extracted from area imageries. In order to conduct a qualitative evaluation, we process the LKISS footprint with our change software and generate the multi-scale building maps at the same scale as our output. And then we compared both the generalized map with the IOU intersection over unions. After that, we find several challenges of this process. First, since our LKISS and our area imageries are not from the same times, there are indeed some changes over time. Some buildings are newly built and some of them are missing. And also we find there's an imperfection of the area imageries. Like on the right side, we can see that it is not a real true auto photos. We can see that there are still inclined wall to be observed on the imagery, which leads to an enlargement of one or two direction of the building shape. And also on the left side, we can observe the building eaves in general larger and which leads to an enlargement of all direction of the building. A possible solution is to neglect the change of individual buildings, such as regard the building has no overlaps on the other data set to be real change, and we only conduct the comparison on this unchanged building. And a possible problem is that the partially changed building cannot be considered. And secondly, in order to consider the imperfection of area imageries and also the building eaves, we have given some tolerance on this evaluation to compare with footprint data with a buffer of 1 meter. As we can see that the compare with the origin and origin, which has considered the building, we can see that around 2 to 3% of value gain can be observed. And also we see that if we considered the buffer of 1 meter, we can see around 5% to 8% IOU gain on this thing. Therefore, we can see that the imperfection of area imagery and the building eaves are much huge challenge than the real changes over time. After perform the change detection to detect the unmapped buildings as we shown in the red vectors. And then we just present the update proposal with a map scale of 1 to 25,000. As a summary, a pipeline method has been developed to generate multi-scale building maps from area imagery, and the output, the building maps are at the scale 1 to 10,000, 1 to 15,000, and 1 to 25,000. We can also perform change detection and provide updates proposal at the desired map scale. As outlooks, we would like to try out just other map features such as line features, road, rivers, and also free shape polygonal features like lakes and park. And we also aim to further investigate the interplay between map features with the deep learning models.